All right, mathletes, here's 2.4, linear functions and models. So what is a linear function? A linear function is a function of the form f of x is equal to mx plus b. The graph of a linear function is a line with a slope m and a y-intercept b. Average rate of change of a linear function. So the linear function has a constant average rate of change. The constant average rate of change of f of x equals mx plus b is m. Notice that your average rate of change is the slope of your line on your graph. So an example, we can have scatter plots, and we're looking to see if it can be modeled with a linear equation. So if I take a line tool and I try and model some of these with a line, it's not going to be very close. Okay, so A, I would say, is not a good fit for a linear application. Neither is C. You can't fit that data. Notice that B is very close to a linear relationship, and if we flip this down here, our D is going to be close to a linear relationship. So for a linear relationship, I'd say this would be no, yes, for these two, and no for these two. So our first example here is a number of cell phone subscribers in millions in the United States from 1990 to 2002. Our input, our X, is the year since 1990. And that data is shown here below. Okay, so as we're doing a scatter plot, our X values, our inputs are typically on our X axis, and our Y is on our dependent variable is on our Y axis. So as we graph this, we're doing years since 1990. So this is going to be at the axis, it's going to be 90. So I'm going to relate this. If I make an X value, this is going to be 0, 2, 4, 96 will be 6, 98 will be 8, 2000 will be 10, 2002 will be 12. So if I label 2, 4, 6, 8, 10, 12 there, and we had a number of cell phone subscribers in millions, so it goes to 127.8 million. So I'm going to go up by 10 million. So this is going to be 20 million, 40 million, 60 million, 80 million, 100 million, 120, 140. So now that I have my scales here, I want to go ahead and draw my points. So I have one at 0 years, I'm about 4.3, so I'm going to be right about there. At 2, I'm going to be 13. I'm going to be right about there. At 4, I'm going to be 29.1, so I'm going to be right about there. At 6, I'm going to be 44, so I'm going to be right about there. And at 69.2 at year 8, 69 is really close to 70, and 102.5 at 10. 2.5 is going to be right around there, and 127.8 in year 12, so 127.8 will be right around there. So I have made my scatter plot. So to draw my line of best fit, I'm just going to estimate here. So I'm going to get my line tool, and I'm going to draw it out, and I'll use red here. So I know my y-intercept here, and I'm just going to try and have it close to as possible to these other lines, to these other points. Okay, so if I bring it to right about there, okay, to find the average rate of change for the line of best fit, I'm going to want to find the slope of this line. So if I estimate these values here, I'm going to estimate that value for simplicity's sakes to be an x of 0 and a y of 5. And I'm going to estimate this point here at the end of being at year 13, x being 13, and my y being 130. So if I go through this, and I can find my line of my slope, my average rate of change here. So average rate of change is change in y over change in x. So this is going to be 5 minus 130 over 0 minus 13. So here I'm going to get negative 125 over negative 13. So that's my rate of change. So if I interpret this, let's go ahead and get rid of our negative values. If I interpret this slope, I can interpret this so my y, my change in y, is number of cell phone users. So and then this x is years. So in 13 years since 1990, I'm going to expect 125 new cell phone users. So that's how I would interpret that. So if I wanted to write an equation for that line of best fit, I can go ahead and use a point that is on that line or my y-intercept. So I'm going to say my line of best fit, I'm going to call it L of x is equal to 125x, 125 over 13x plus my y-intercept of 5. Okay, so that's my line of best fit there. So now, using my LX, I want to make a prediction, let's say in 2011. So remember this data, my X's were defined from years since 1990. So 2011 minus 1990, I'm going to have 21. So I want to know when L of 21, evaluate this function at 21. So I do 125 over 13 times 21 plus 5. Pull out my calculator, and I get 125 times 21 divided by 13 plus 5. And I see that I would have approximately 206.9 million cell phone subscribers. Okay, so that was just eyeballing with the graph. We can also do this with our graphing calculator. Make sure you get these notes down in the here in the purple. This is going to outline how we're going to use our linear regression function in our graphing calculator. So in order to do this, the first thing we want to do is we want to put our L1 and our X's in L1 and our Y's in L2. So step 1 says you hit stat. You want to edit, so you hit enter and go ahead and put the values in from our previous table into our calculator. I've already done so here. Okay, so pause the video if you need to take a second to do that. After you've inserted those X values in L1, the X values in L2, what we want to do is we want to go to step 3 and we want to hit stat, and we want to go over to calc, and we want to calc a linear regression. That's number 4. And then you hit enter. And you get the equation for the line of best fit. So I'm going to write, I get 10.5 rounded to 3x minus 7.5 as my y-intercept. So I'm going to go ahead and plug in those values into my y equals. So I'm going to clear this out. I'm going to clear this out. And my y equals, so I'm going to have 10 6.53 x minus 7.5. Okay, so what I want to do next is I want to turn on my stat plots. So my stat plots is up here on the top of my y equals. So it's in blue, so I got to hit second, y equals. My stat plots I need to turn on, so I'm going to hit 1. So I'm going to scroll down and say, all right, I want this on, so I hit enter. I want a scattered plot, so I'm going to leave that highlighted. My X list is an L1 and my Y list is an L2, and I'm fine with those markers. Next piece here is I want my window to be appropriate. Okay, so I'm going to quit out of this, and I want to type in my window. I'm not dealing with negative X values, and I knew I went up to 21 years in 2011. Let's just go up to 30 years there. And a scale of, let's say, 5 is fine. A Y minimum, we're not dealing with negative cell phone subscribers. And then we got up to, well, 206 million. So let's go up to 300 here and have a Y scale of, let's say, 50. Okay, so now when I hit graph, notice I have my scatter plot and my line of best fit, and it's nice because it looks like I know I'm accurate here because it looks like it's fitting that data pretty quick. So let's see how close we were with ours. So in 2011 we had about 206 million estimated with our line of best fit. So if I hit trace, so right now in the top left corner I have P1 equals L1, L2. I don't want to trace my stat plot, so I hit down on my feature and I'm going to trace this line. So I'm going to trace it and I'm going to type in 21 and I see it's 213.63 million. So the equation that I found was pretty darn close to the one that our calculator found as well. So make sure you have any questions written down with using your calculator to find linear regression lines. All right, so the next piece here, break-even analysis. It's the same as our supply and demand problems. The shoe company invests $300,000 in equipment to produce a new line of athletic footwear. Each pair of shoes costs $5 to produce and is sold for $60. How many pairs of shoes must be sold before the business breaks even? First part is create an equation representing the total cost. So I'm going to use C of X as my function, so it's representing cost. So I have my initial cost of $300,000 set up plus $5 per shoe I make. So 5, so I'm letting X equals number of shoes. Okay, so this cost function, the C of X, is going to give me the cost for how many shoes I make. So my revenue function, I'm going to do R of X, okay, is a function defining how much money I'm going to make. So I make $60 per every shoe I make. Okay. Part C says solve the problem by figuring out when the total cost is equal to the total revenue. In other words, what is my break-even point? Okay, so I'm going to kind of go over here and use this space to set up an equation. So the break-even point, I'm just going to set these equal to each other. 60x is equal to 5x plus 300,000. We're going to subtract 5x from both sides, and you can see we get 55x equals 300,000. Now at this point in the equation, you can kind of think to yourself, well, yeah, if they're spending $5 per shoe and they're getting $60, they're making $55 per shoe. So how long is it going to take for them to make that money up, that $300,000 for the factory? Well, we divide that out by 55. So I can get my calculator out and I can do 300,000 divided by 55, and I see that I'm going to need 54, 54. 54.54, repeating number of shoes until I break even. Okay. Part D, write an inequality to describe how many shoes must be sold in order for the shoe company to make a profit. So that inequality, so when X is greater than, so at 5454, we're going to be not quite enough money to make it. So we need to make, because we're not going to make 0.5 amount of shoes, so I got to put this in context. I need shoes to be 5455, number of shoes that I need in order to start making a profit. Okay, so let's look at our last example here. So continue using this equation that we found in the previous. If the shoe company spent a total of $750,000, how many shoes did they produce? So I'm going to go ahead and use my cost equation. So I'm saying my cost is $750,000, and that's equal to the $300,000 we put in initially plus the 5x. So to solve this, we subtract 300,000 from both. I'm going to get 450,000 equals 5x, and divide both by 5. And I'm going to see that x is equal to 90,000 shoes that they produced. So if the shoe company produced 100 shoes, how much revenue would that generate? So I'm going to use my R equation, and I am producing 1,000 shoes. So how much revenue am I going to produce? Okay, I'm going to produce $60,000 after producing 1,000 pairs of shoes. Okay, so our last example here, straight line depreciation. Suppose a company has just purchased a new computer for $3,000. The company chooses to depreciate the computer using the straight line method over 6 years. So that means I can do 3,000 divided by 6. That's going to tell me how much the computer depreciates each year. So if I come up here and I say this is 1,000, that's 2,000, that's 3,000, that's where the value of the computer starts at year 0. So I can think of that as a point here. Okay, so after 6 years, so 1, 2, 3, 4, 5, 6. After 6 years, the value of that computer is going to be 0. Okay, so if I want to write a linear function that expresses the book value of the computer as a function of its age, I want an equation of the line represented here. Okay, so I can use those 2 points that I know. At time 0, it's 3,000, and at time 6, it's equal to 0. So I have my intercepts. So easiest thing to do here is just find my slope. So I'm going to have 3,000 minus 0 over 6 minus 0. Well, that's 500 there. And I know my y-intercept is 3,000. So I get y equals, and it's negative, my depreciation. So this should have been 0 minus 6. I get negative 500. It's a negative slope. So negative $500. X being every year. And I started at $3,000. Okay. I graphed the linear functions. What is the book value of the computer after 2 years? So if I rewrite this in functional notation, f of x. So F at 2 is equal to negative 500 times 2 plus 3,000. So I'm going to see that is equal to $2,000 after 2 years. Okay. Well, when will the computer be worth 2,000? Well, we just answered that. So the computer will be worth 2,000 after 2 years. All right, that's our notes for tonight. Make sure you highlight any questions you have, and I'll see you in class later.